Good morning, everyone. It is my pleasure today to introduce our speaker of the day to the Netpore webinar. Our speaker this morning is Harry Borenstein. Dr. Borenstein finished his PhD in chemistry with distinction at Bar Ilan University in 2016. His research deals with carbon-based material for super and pseudo capacitors. Then he received the Israeli Ministry of Energy postdoc fellowship, which he conducted at UCLA in USA, where he further developed carbon-based nanomaterials for energy systems. Dr. Borenstein's work received the appropriate recognition from the scientific community, and Harry has won several awards and fellowships, including the Sharp Fund for Excellent Researchers at the UCLA BIU Fellowship. In 2020, Harry joined the Department of Chemical Science at Ariel University, where he established the Nanocarbon and Composites Lab. It investigates different topics in material sciences, including carbon-based nanomaterials for energy systems, laser-assisted fabrication of 3D graphene, electrocatalysis of hydrogen, ammonia, CO2, and much more. And it's our pleasure, and my pleasure in particular, to let you start your presentation, Harry, please, on recent progress in laser processing.
Yes, so thank you very much for the invitation and the presentation. We will have to do it the old-fashioned presentation without any animation and all the other tricky things, but the science will still be there. So I hope this message will work. Yes, so this is a webinar with Netpore. I would just say that this is following a short visit term that I did, funded by Netpore in Imperial College in London with Dr. Andreas Kafizas. So I'm very grateful for this funding. Shortly on where is the university. It was supposed to be step by step, but this is Israel. It's a very small country, and Ariel is almost in the center of Israel. This is on the mountain, so the view is very nice, and we are very close to Shomron, which is in one of the ancient capitals of the Kingdom of Israel, backing almost 3,000 years ago. So the university is on the very top of the hill, and here we have the building of the chemistry building, and this is where my group is. And I call the group nanocarbons and composites. You can find the website in Google, just Borenstein Lab. So the research is focused on nanocarbons, and we do carbons in different methods, also the traditional methods, heating up in a furnace for 2,000 degrees under inert atmosphere. But today what I want to show you is the more unique synthesis method that we are focusing, and this is the laser fabrication, laser-induced graphene, we call it. So we do laser-modified materials, not only graphene, different materials, some sustainability research, a lot of electrocatalysis like CO2 reduction, methanol oxidation, water splitting. We also, as a chemist, I'm more focused on developing new materials, not the application. This is for the funding. So We have a lot of carbons and nanocarbons based composites. I will show you a few examples today, and also on energy storage devices, batteries, supercapacitors. Um, this is the very broad view of what we do. And today we will focus on the research in laser. So what is exactly laser? Let's start before why we need the laser. So, and this is most of the laser modified materials that we do are carbon based. So we produce graphene with laser. So we'll start with what is good, why graphene is so important. Uh, and I'm sure I don't need to explain this to you. We're just reminding everyone that graphene is one, you could call it ultimate or super material with a lot of uh, very good properties that as an engineer you would like to have in every material that you work with. It is very conductive, maybe the highest conductivity, uh, very high surface area, very light, strong and flexible. It is so strong and light that people would even suggest to make this. I remember even as a child or as a teenager, when graphene was only at the very beginning, right after the Nobel Prize, that everyone got familiar with that. People would believe that it will revenue the entire material science and material industry, and dreamed about crazy things like uh, binding the moon to Earth with a graphene cable. So we have all of these crazy properties, but the question is why we didn't reach it, right? We don't have graphene everywhere around us. It is very rare and very expensive. And the answer is that it is very difficult to produce high quality of graphene in large quantities. Basically, whether you use very expensive method like CVD, and you have the very small amount of graphene, monolayered graphene, where all these properties, physical and chemical properties, are preserved, or you use other methods like wet chemistry, and usually you don't get graphene. You end up with very defected graphene or something that is more like graphite. At the beginning, we tried to order graphene from commercial suppliers. I don't want to mention names, but if you put it in XRD, if you put it in Raman, you see that it is not actually a graphene. It is more like amorphous carbon, graphite. So we had to start making our own graphene. And one of the, I think, most promising method to produce highly graphitized graphene with high quality and relatively easy is with laser. So how exactly it is made? The idea is very simple. You just take a carbon precursor. Not all carbon precursor could work, and we'll talk about that later, but you just make a dry film of graphene, and you just laser it, and you end up with graphitic film. I'll show you more characterization and images in a minute, but the mechanism is quite simple. The laser that we use is CO2 laser that simply heats up the sample very fast and very locally. It could reach very high temperatures, up to 2000 degrees, and the carbon is simply carbonized and graphitized into graphene. By the way, you can feel free to interrupt with questions whenever you would like. Um, you, if you have a question, just ask it. Okay, and so this is what we get. Okay, this is an SEM image, and you can see there are very large gaps between the graphene and layers of graphene particles, and the reason is because a lot of gas is released during this thermal reaction. A lot of CO, CO2, oxygen, hydrogen gases are formed very extensively and create extensive pressure and simply break apart the layers. So we end up with very developed porosity, very large meso and down to micropores of the materials. And if you take a closer look on the edges of the particles, it is facing up to the microscope, you could see the layered material of the 2D graphene. And this is TEM, which is isolated single layered of graphene. It is quite transparent. And how do we know it is graphene? We just take it to spectroscopy. In XPX, you can see the black curve is for the GO. This is one of the precursors that we use. GO is, of course, graphene oxide. So it is an oxidized graphite, layers of graphene, oxygen, and then other graphene. But then you have to do two things: to exfoliate it and to reduce it, meaning to eliminate the oxygen out. And this is what the laser do. As we use stronger powers of the laser, you can see that the peak of the CO is lowered, and we are left with one peak that is getting narrow around the sp2 carbon. And Raman, which is also a very strong, very, very powerful tool for carbon characterization, also shows us very high graphene. You see that the D to G ratio and also the 2D band show very high graphitization level. We can control the graphitization level, the conductivity, the surface area by changing different parameters in the laser. For example, laser power, the speed of the laser, the environment, and other things. But anyway, we end up with graphene. So you could do, basically it is a thermal reaction. So you could do it also in a furnace. The question is why we need this laser and not just put it in a furnace. And the answer number one is very simple: production. And I will elaborate it in a second. But very unique advantages is one, you can directly print it on any substrate. Meaning, in order to create graphene, you need very high temperatures. If you want to use graphene on plastic substrates, if you want to print carbon-based electronics, if you want antibacterial coatings, whatever application on plastics, you cannot directly create the graphene on it because the plastic is thermal sensitive. So you have to prepare the graphene separately and then print it on it. The laser offers, I think, the only way to directly form the graphene on whatever substrate, because the heat comes from one direction, and if you turn it properly, you can just impact the carbon and not the substrate underneath it. Okay, so we can, and this is what we do. We have some microelectronic projects where we directly prepare the graphene on the plastic, and you will see a video showcasing this in a minute. So this is one big advantage. And another one is a patterning. With the laser, we can pattern whatever shape that we want, whatever size that we want. And it is also very beneficial for many applications. All these three are advantages in terms of fabrication, but also chemistry-wise, the laser give us very unique phases. We call it metastable phases, because the heating up and cooling down is very fast and very local. Only the diameter of the laser beam is heated up. uh, you don't get necessarily the most stable phase, okay? And I will show you a lot of examples for this later. So we end up with very unique chemistries, very unique material that you will not achieve if you just put it, for 10 hours in a furnace where everything reaches the most stable phase. Okay, so that should be the translator to the easy production, and this is a very short video that I will show you how we make it. So we take the carbon precursor. In this case, it is carbon nanodots. I will show it also later. And with Dr. Blade, we prepare the thickness. It is very important because of the thickness of the penetration of the laser beam. And that's it. Now it is one step lasering. Maybe you could see it is a little small, but I hope you could see the change in color where the laser irradiated the oxidized carbon, and now we can wash away. The oxidized carbon is hydrophilic, it is washed away, and the graphene remains on the plastic, and we can make electrode. It is very conductive. Okay, this movie is done by my friend and colleague Volker Strauss from Max Planck Institute. And so all these advantages you've seen in the movie, it is very fast. In just seconds, you can have the graphene instead of a lot of hours. Everything is done in ambient conditions. You don't need inert atmosphere. And why is that? Because if you heat up carbon in any form more than 300, 500 degrees Celsius, it will burn off in the presence of oxygen, right? But with the laser, the reaction is so fast, it's happening in milliseconds, so that the oxygen is eliminated and the exposed carbon just form a very fast bond to whatever and other carbon that is next to them instead of oxidizing. Okay, so the kinetics of the graphitization in this case, it is faster than oxidation or burning of the carbon, and this is why it can be done in ambient condition. It is of course energy efficient, very fast, very small electricity that is consumed by the laser instead of a furnace. We don't have any waste. Okay, it's not a wet chemistry. We don't have any solvents. It is also very safe and scalable. You can do. It is scalable in terms of XY directions. Okay, not Z direction. This is limited to let's say couple of tens of microns, but areal size could be as large as your laser is. Okay. Now we have to keep in mind that not all carbon precursors, not all carbon materials can undergo this graphitization process with the laser. So in fact, there was one lab of James Storr that they published a paper with 15 different polymers, and only 2 of them could generate graphene. And it turns out that what you need in order to form graphene is a beginning, let's say, a seed of graphitic or aromatic carbon, and this is what the first precursor was uh, GO, graphene oxide, and polyimide, a lot of polyimides because you already have these aromatic rings, but yet not all of them could overgo this later processing. For example, carbon nanotubes that we tried didn't go. So the other component that you need is functional groups on the surface of your material that will react with the laser. So again, if the mechanism is elimination of functional groups, heteroatoms, oxygen, nitrogen, hydrogen, exposing carbon atoms to form sp2 carbon-carbon bond. Okay, this is the mechanism. So we need these two properties. Uh, and then in the last 5 years, what we did in my lab, and other people did it as well, is trying to widen the library of material that can overgo this reaction beyond GO, beyond polyimides. And one of the materials that I love very much, I like very much, is carbon nanodots. And this is also Volker's idea. And the reason is that carbon nanodots are probably the smallest graphitic allotropes. They have very special structure where they have in the core they have graphitic structure, sp2 carbon. It's a little amorphous sp2 carbon, but on the surface they are coated with functional groups. You can see here a TEM of the nanodots, very small, down to maybe 2 nanometers, very easy to produce. They are fluorescent because of the functional groups on the surface. So they could be very good candidates to undergo the laser reaction. And indeed, if you put them under laser, you will get graphene films. But look, let's say the macrostructure, the morphology of these films are very different. You see that it's like a sponge-like. This is an SEM, and in TEM you see it's like honeycomb structure. And so it is very different in morphology than what I showed you before the polyimide or graphene oxide. And the reason is we used the smallest building blocks that are possible out there. So the graphitic cores of these nanodots, carbon nanodots, are integrated together to form larger graphene particles. Okay, so the holes here are the pressure that caused the released gases, but the walls of these compartments of these bubbles is made up of graphene, and we could isolate a single graphene sheet. In TEM, it looks very similar to the graphene that I showed you before, made of the graphene oxide. It is much more crumbled, again, because it is made of the smallest building blocks. But in spectroscopy, you could still see that it is graphene. Again, in XPS, the CO peak is eliminated, and we end up with the sp2 carbon. And also in Raman, this is a little more complicated, and I don't want to spend time on this. I just show you a very quick application that we could use this graphene out of the reduced carbon nanodots. This is the RC, and these reduced carbon nanodots. And this is electrodes for supercapacitor. So I did my PhD in electrochemistry department, electrochemistry group, and supercapacitors are very popular. People just take whatever new material that they do and they put it in a beaker with electrolyte and charge it and discharge it. Uh, just I want to show you one thing, if you could. So this is a CV, and I'm sure you all know that the CV is a scan of potentials. Where you see a redox, it is like spectroscopy. You scan the potentials, and whatever potential that you have any redox reaction, you will have very high current, positive or negative current. Here we see the scan of potential. We don't see any peak, and the reason is there is absolutely no redox reaction. And why that? Because we are left with only graphitic carbon. It is inert electrochemistry, so we don't see any peaks. And we could cycle the supercapacitor very fast. It is actually, if you see it, 10 volts per second. It is considered to be very high. It is maybe 100 times faster than conventional activated carbon that we have in commercial supercapacitors, and we'll talk about it later on. Okay, so this is a very good result that are made only because of the special structure that could be achieved by using the smallest building blocks, the carbon nanodots. Okay, any questions until now? All right. I now want to show you two very nice, I think, applications that we use these laser, and could be achieved due to the very special synthesis method. And one is for flexible electronics. Okay, so flexible electronic, wearable electronics. Now it is very hot issue. It is a lot of buzz, and the problem is that if you just take a regular conductor made out of nanoparticles, when you bend it or stretch it, the conductivity changes a lot. Okay, it could, because when you bend it, for example, you separate let's say graphene particles one from another, the conductivity decreases. Okay, just fell down. And when you compress it, it is increasing. This is also not very good, increasing the conductivity. For electronic devices, you need a very stable conductivity. So what we did, we mixed the graphene with carbon nanotubes. Okay, so we simply mixed graphene oxide with carbon nanotubes, overwent very special chemical modification that we just added on the carbon nanotubes, these functional groups that we talked about that will react with the laser, otherwise it is work. And you see in the microscope images that we have the graphene sheets, and in between the sheets we have the nanotubes. Okay, and the idea is that the nanotubes interconnect the particles of the graphene. Okay, so in case of stretching or bending, that the particles are being separated, the nanotubes will restrain the conductivity. And this is indeed what is happening. Okay, hope you can see. So what we did here is we directly printed this graphene on nitrile glove. Okay, I told you we can do it on any substrate. And when it is bended, right, my student Ashmita's finger bended her finger, you saw that the conductivity didn't change much. Okay, so we can bend it negatively and positively. Okay, and you see that the change is not very significant. So we can keep that conductivity even on a flexible substrate. And this is achieved with the laser. Again, directly printed on any substrate. And not only conductivity, but also if you want to have microelectronic devices with an energy storage component inside, you can use supercapacitors. So this is a supercapacitors made with RGO. So you see the big difference in the incapacitance with and without. I mean, in bending and flat conditions. Okay, so we have a very large decrease in capacitance. But when you add carbon nanotubes, not a lot of, even only 1%, you can restrain almost the entire capacity retention, okay? Even if you bend it 90 degrees, okay? And it is also very stable. I mean, even after hundreds of times of bending, it still restrain the capacitance. So this is one thing that I wanted to show you. Another thing is we call it laser healing of graphene with carbon nanodots. So one problem of graphene is that it could react with the oxygen in atmosphere, and after a while, it loses all its beneficial properties. We have a device with graphene, and it is out there, it is exposed to air, exposed to humidity, exposed to sunlight, and you see decrease in performances. We have a solution for that. You can take carbon nanodots. Okay, so we already have the RGO film. We take suspension of carbon nanodots. Sorry. Okay, and we add it to the film, and then we lay both of them together, and we see sharp increase in all the properties of the graphene. And how it is done, this is an illustration. We have the damaged graphene. You see it is breaking here, broken. And we have the nanodots. And the nanodots are attached mainly to the defected parts of the graphene, obviously, because of the functional groups. Then when we laser it, the nanodots are basically patching the graphene back together. So now it is an integrated graphene sheet, and all the advantages, properties are restrained, high capacity, high conductivity. You see that this is again Raman is increased again, and it is now the supercapacitors were actually so fast that we could use it. Probably we are working on it to improve it even a little further more as AC line filtration. So I don't getting too much into it because I want to show you one last thing. But AC line filtrations are a component that we have in any electronic devices. Nowadays, they are used with just regular um, um, physical capacitor, okay, not electrochemical capacitor, which means that the capacitance is very, very low. And the reason for that, you need very fast response, charge and discharge. And with these electrodes, we could get very close to the response time, response rate that is needed for these devices. So this is also very promising, very interesting. Yeah. Okay. So until now, we talked only about carbon, right? But we don't do only nanocarbons. The lab is nanocarbons and composites. So now I'll show you something that we also focused the last few years with metals. But to start with that, let's just say that not everything is so green. We don't have only advantages in laser processing, but also some complexity. For example, the heating is never is uneven. Okay, when the laser comes from one direction, the upper part of the film is heated much more than the lower part of the film, right? So it is not uniform. Also, the fact that the reason that this reaction is so fast, it may be good for some things, but it is not very good for other things. It is very hard to track. Okay, we can in milliseconds you cannot track, the changes in chemistry or the chemical structure changes during the reaction. So it is hard to understand. We get multiple oxidation state, and it is not very easy to control what oxidation state will end up with, and I will show you that right now. And we get what the metastable phases. This one was also in the green screen of the advantages. Sometimes it is not very much advantage, and this is done. Okay, I will make this a little short because not to make this lecture too long, but this is wonderful. You take this is we took a cross section with a resin, cross section of the graphene loaded on polymer or plastic substrate. So this is the graphene film, and this is just photo image, right? With optical camera. And now you see that we wanted to see the changes in chemistry throughout the depth of the film. So we see that the carbon, nitrogen, oxygen content, nitrogen is, and also oxygen, but for sure nitrogen, almost entirely on the lower part of the film. Okay, the upper part that that gets all the heating from the laser, all the nitrogen eliminated. So this is why you have a very complex, and the porosity is very different throughout the depth of the film. So it is very heterogeneous chemically, and also the structure is very heterogeneous. So okay, so then we wanted to make the material more interesting, not only carbon. So we added with other things like metals. When you mix the carbon precursors with metal salts and laser it, two things happen simultaneously. It's very interesting. The carbon is being reduced, but at the same time, the metals are being oxidized or form metal oxide, nanoparticles. Okay, so if you mix it and laser it together, you will have, you see this is a graphene and it is doped with metal nanoparticles. This is iron oxide nanoparticles. And you clearly see in a CV, you can clearly see the redox peaks. Remember that flat CV that we saw for only carbon? Now with oxygen, we see clearly the redox peaks because we have redox active material there. And this opens really a lot of opportunities, almost endless options of what you want to do with these materials once you introduce the carbon with other materials. Okay. And there are many factors that you could change in order to control whatever metal you will end up with, because some metals end up with, we have now metallic nanoparticles. For some experiments, we get metal oxides, we get metal nitrate, uh, different oxidation state of metal oxides. And we wanted to understand how we can control, how can you anticipate what will be the product of this reaction. So the environment composition for sure influence, meaning how much oxygen do you have in the precursor, how much nitrogen you have, uh, the metal concentration in the for sure depend with the particle size, okay, because basically it is just in nanomaterial course 101, they tell you the nucleation and growth, okay, directly depend on concentration of how much metal you have there. Okay, and also we saw this in a paper showing manganese oxide MnO and Mn3O4 at the very same single particle, the same experience the same uh, heat, the same laser radiation. You have different phases of the metal. And so to understand it, there are many factors, but just the basic question is, if you have redox reaction, if something is being oxidized, something must be reduced. So what is reduced or what is being oxidized? And the answer is, I will just skip to the answer, is that the carbon is actually disproportionate. Some of the carbon is oxidized and leaves as CO2 gas, and some of it is reduced into graphitic carbon, and at the same time, these carbons could oxidize or reduce the metals, and then, like all redox reaction, it has to follow the reduction potential of each reaction. Okay, so this is a perspective that it is now under review. But if you take, we screened about 23 papers and our own experiments with different metals, and you can. So here you have the reduction potential of the reaction, and here you have the oxidation state of the final product, and you can see a very clear, almost linear relations that materials with relatively negative reduction potentials like manganese, molybdenum, zinc, iron, they all end up with high oxidation states. And of course, metals with very positive redox potential like platinum, gold, ended up in zero state, meaning metallic oxidation state. Okay, this was just two applications, and I will finish with it. We have two more slides. So one is the we used iron oxide in order to electrocatalyzed OER. Okay, so we have very nice result with this. And also for CO2 electroreduction, we use, of course, copper. So we have copper nanoparticles in this graphitic matrix, and you see the onset potential. If we added the CO2, dramatically going down. Okay, so I will finish with that. I don't want to talk too much, and we will leave maybe some time for questions. So thank you very much for listening. This is the group, some of the students, and some of our collaborators. And I cannot finish without mentioning the somber university that we had here in Israel 3 days ago. Still in the middle of war. We all pray for peace to come for this region very fast. Uh, but for this, we have to save these lives, these hostages taking captive to Gaza. We all pray for their safe return very soon. So thank you very much.
Thank you very much, Ari, for your nice presentation and kind words at the end and peace message. It's very interesting approach that you have with your for graphene and preparation. So we have a few minutes for question. So please, if you have any question in the audience, you can either just start speaking or raise your hand if you prefer. It's uh, it's open. No, so I may start uh, if uh, if you don't mind.
Yeah,
We start with the question. So you mentioned for your preparation that you need both ingredients, two ingredients, the graffiti core and the functional group.
yeah,
Uh, and so I was curious. You probably explained it, but I'm maybe I need more information, and maybe I misunderstood the role of the functional group
yeah,
in this. And the second part of the question is there any difference observed depending on the functional group and how you can orientate your synthesis changing this functional group?
yeah. Okay, so thank you for this question. Uh, um, what I mean, it's not two ingredients, but what it's two components of the same material. Okay, so we had to have in this material we had to have a carbon or graphitic backbone, let's say that way. Okay, so that will serve as a seed for nucleation and later growth of the graphene. But what we need, the other component is the functional groups that, so what happens once the laser hits the material? Um, the first bond to be broken are the weakest one, and this is usually between the carbon, the graphitic carbon, and oxygen, nitrogen, hydrogen. Okay, this is what I called functional groups. Once they leave, okay, this bond is broken, the carbon atoms is is free to form another S2 bond with a neighbor carbon exposed carbon atom. Okay, and this what creates the integration of the seeds to form larger graphene particle.
Thank you. I get it. Yeah, I guess I didn't get the point. So it means that if you have the better the coverage is with the functional group and the better the or not really.
So it's a little trade-off because if you have too much of heteroatoms and too less of seeds, what will happen is the laser will just burn everything up. And okay, so we remain with almost nothing. Okay, this also happens if you use too high laser power. Okay, so you have to be very careful with that, but the two components are very important.
Okay, so yeah, this is a very precise optimization of your surface. And do you have observe any difference whether you use a carboxylic acid or an OH group, for instance?
Yeah, so for example, if you want to use, and we did that, I didn't show it. If you want to use n-doped carbon or even s-doped carbon, you can start with precursor that already have nitrogen in it. For example, the carbon nanodots are n-doped because we used urea with the nitrogen, okay, as a precursor to the carbon. So we have already the nitrogen in it when we try to build the larger graphene particles. So you can play with that. This is another option. You know, as chemists, we like to play with materials, and yeah, it's open you new options to end up with another final product.
Okay, thank you. Thank you very much. It's again, it's very very interesting. It opens so many possibilities of designing materials and of course for the different applications. It's very very nice. Um, is there any question? Other question here? So if not, thank you again, Eric, for your presentation today, for accepting our invitation to
Yes.
present your very nice work in your lab.
Okay. Thank
And
you very much for.
wish you and all of the people here, wishing you a very, very nice afternoon and week, and hope to interact again sometime soon. Thank you
Yeah.
very much.
Yeah.
Have a great day.
Yes. I just if can ask